Well, good morning, good afternoon, good evening, whenever you might be listening or watching this. So last week, I kind of threw a lot of generalities at you, getting you prepared to really get into the meat and potatoes of aviation weather and what we are going to learn in this class. So this week, we're going to really start going down to individualized things, okay? So as you can see up here today, we're going to go over thunderstorms. Now, thunderstorms is a big deal, and you will have to really know what you're doing in trying to circumnavigate thunderstorms, as you will see as we go through this. So without further ado, let's jump right into this, and let's see about teaching you about thunderstorms, okay? So first of all, what we're going to look at is thunderstorm terminology. So I'm going to blow this up so you can see it and I can see it and we can discuss it, okay? So let's look at thunderstorm terminology. The anvil. Now you will need to know what an anvil of a thunderstorm is, and it will come in very handy for your piloting abilities. So the anvil of a thunderstorm is the flat, spreading top of a cumulonimbus cloud, often shaped like an anvil, hence the name. Thunderstorm anvils may spread hundreds of miles downwind from the thunderstorm itself and sometimes may spread upwind. A bow echo. A bow echo is a radar echo that is linear but is bent outward in a bow shape. And the reason that this linear line of storms bends outward in a bow shape is normally because of heavy straight line winds. A derecho. A derecho is a widespread, long-lived, straight line windstorm that is associated with a fast-moving band of severe thunderstorms. Now, most of you have probably lived through a derecho before. You may not remember it, but they do come through Arkansas every couple of years. Now, if you've been impacted by it and you're old enough to remember it, you'll remember that it's pretty wicked, and it will definitely leave a mark on you if you live through one. So a downdraft. A downdraft is a small-scale column of air that rapidly sinks towards the ground, usually accompanied by precipitation, as in a shower or a thunderstorm. A microburst is the result of a strong downdraft, and we will cover microburst in just a little bit. A gust front. A gust front is the leading edge of gusty surface winds from a thunderstorm downdraft. Sometimes associated with a shelf cloud or a roll cloud, it may also be referred to as a gustnado or an outflow boundary, and I guarantee you have experienced a gust front if you have lived in Arkansas for any length of time. So let's talk about a mesoscale convective system, otherwise known as an MCS. This is a complex of multiple thunderstorms that become organized on a scale larger than individual thunderstorms, but smaller than extratropical cyclones. Now, normally these persist for several hours or more. We get MCS thunderstorms through here quite often. A roll cloud. A roll cloud is a low, horizontal, tube-shaped Arcus cloud associated with a thunderstorm gust front. A roll cloud are relatively rare. They are completely detached from the thunderstorm base or other cloud features, thus differentiating them from the more familiar shelf clouds. So here's something we're all familiar with, and that is a severe thunderstorm. A severe thunderstorm is a thunderstorm that produces hail with a diameter of 1 inch, that's a quarter size, or larger, convective winds of 50 knots, 58 miles per hour or greater, and or tornadoes. Now, for a thunderstorm to be classified as a severe thunderstorm, one of these conditions here has to be present. They do not all have to be present, only one, okay? A shelf cloud. Now, a shelf cloud is a low, horizontal, wedge-shaped cloud associated with a thunderstorm gust front. Now, unlike a roll cloud, a shelf cloud is attached to the base of the parent cloud above it, which is usually a thunderstorm. So if you see a shelf cloud, they're very easy to tell apart from a roll cloud. A roll cloud looks like a tube. It looks like the tube that your paper towels come on. All right? It's circular like that. It looks like a tube. Now, a shelf cloud looks like a bookshelf, and the shelf cloud is attached to the storm. A roll cloud is not. So here's a term that you need to be familiar with: updraft. Now, an updraft is a small scale current of rising air. If the air is sufficiently moist, then the moisture condenses to become a cumulus cloud or an individual tower of a towering cumulus or cumulonimbus cloud. Now, you will see in just a few minutes that the towering cumulus is one of the stages of a thunderstorm. So without updraft, you do not have a towering cumulus. Without a towering cumulus, you do not have a thunderstorm. Okay? Here's something else you need to be very familiar with: a microburst. Now, a microburst is a downdraft, just sinking air, in a thunderstorm that is less than 2.5 miles in scale and lasts anywhere from 3 to 7 minutes. When microbursts cover a large area or last for more than 7 minutes, they can do this, but it's very, very rare. On rare occasions, microburst or downburst can have wind speeds in excess of 150 miles an hour, and that equates to around 13,000 feet per minute. Now, I want you to picture that you taking that little 172 and flying into this. Your little 172 is not going to handle 13,000 feet per minute. Okay? You're going to be in a very precarious situation very quickly. So we need to learn about these so we can stay away from them. All right, so now I'm going to switch back over. Let's talk about the necessary ingredients for a thunderstorm cell to develop. Now, for a thunderstorm cell to develop, it has to have 3 ingredients, okay? It has to have sufficient water vapor, unstable air, and a lifting mechanism. Without any of these, you do not have a thunderstorm, okay? Sufficient water vapor, commonly measured in dew point, must be present to produce unstable air. Virtually all showers and thunderstorms form in air masses that is classified as conditionally unstable. A conditionally unstable air mass needs a lifting mechanism strong enough to release the instability. Now, let me blow this up here so you can see it well. So necessary ingredients for thunderstorm formation, like we said, we got to have sufficient moisture, unstable air, and a lifting mechanism. So the lifting mechanisms include, it could be any of these. It could be converging winds from, or converging winds around a surface low or trough. It could be fronts, upslope flow, dry lines, outflow boundaries generated by prior storms. Local winds such as sea breeze, lake breeze, land breeze, and valley breeze circulations. But these 3 things must be present for a thunderstorm to form: water vapor, unstable atmosphere, and a lifting mechanism. You need to remember these, okay? Not only are you very likely to see these on a quiz or an exam for this class, but you will need to be able to explain what is needed for a thunderstorm in the pursuit of your private pilot license, okay? So, thunderstorm cells, they go through life cycles just like anything, okay? Now, This is a convective cell of cumulonimbus clouds having lightning and thunder. That's very important. You cannot have a thunderstorm without lightning and thunder. Can't happen. What happens when lightning strikes? Well, when lightning strikes, it expands the air around it. If you got a picture in your mind how hot that lightning bolt is. Well, when that lightning bolt comes down through the atmosphere, the air around it is superheated and it expands really quick and then it collapses as it cools off. That collapsing of the air is your thunder. So without lightning, you do not have thunder. Without thunder, you do not have a thunderstorm. Hence the name thunderstorm. Now, a thunderstorm cell, it goes through three very distinct stages during its life cycle. The towering cumulus stage, which is what we referred to earlier, the mature stage, and the dissipating stage. The total life cycle of a thunderstorm is typically somewhere around 30 minutes. It's not very long-lived at all. The distinguishing feature of the towering cumulus stage is a strong convective updraft, which is what we talked about in the previous slide. You have to have an updraft or lifting mechanism forcing that unstable air up, and all that does is takes a bubble of warm, rising, unstable air, and it forces it up, and it's concentrated at the top of the cloud. Now, when this happens, it leaves a cloudy trail in its wake. Updrafts, now this is very important too. Updrafts can reach speeds of somewhere around 3,000 feet per minute. Again, picture your little 172. Your little 172 is not going to handle 3,000 feet a minute very well at all. So you need to know these cycles. You need to know the different stages of these so you can avoid them. All right? Now the cell transitions into the mature stage as soon as rain hits the Earth's surface. Okay? So as soon as rain reaches the Earth's surface, it's in the mature stage of the thunderstorm. Precipitation descends through the cloud and drags the adjacent air with it, and that creates a strong downdraft right beside the updraft. So if you'll picture, you got the updraft coming down and the downdraft coming down right beside it. So imagine flying that little 173 and then it's not going to work well for you, okay? So you need to know what these are so you can avoid them. Now, once the downdraft hits the ground, it spreads out along the surface well in advance of the parent thunderstorm cell as a mass of cool, gusty air. This is that gust front that we were speaking of. So I want you to think of a time when you've been outside and there's been thunderstorms in the area, and then all of a sudden it just seems like out of nowhere, really cool, gusty winds come through, and then not very long after that, it's storming. That cool, gusty air that you felt, that is the gust front, okay? Now this gust front is an arc-shaped leading edge of the downdraft, and it kind of sort of resembles a cold front. So a cold front, if you'll notice when we start studying charts, a cold front is normally arced like this. Well, this gust front, it'll be arced as well. It resembles a cold front, but it's not a cold front, okay? So uplift along the gust front may trigger the formation of new thunderstorm cells, sometimes well ahead of the main thunderstorm. Cumulonimbus tops frequently penetrate into the lower stratosphere and as an overshooting top, where strong winds aloft distort the cloud into an anvil shape. Weather hazards reach peak intensity in a thunderstorm towards the end of the mature stage. Now, here's a piece of information that you need to be familiar with, and you need to really, really know this. Okay, so as you're flying, a lot of times you will see way off in the distance a thunderstorm with an anvil top. Now, whichever way that anvil top is pointing, that's the way that thunderstorm is moving. because as that overshooting top goes into the stratosphere, whichever the way the winds are blowing it, it's going to shear the top of that cloud off and go in that direction, okay? So if you're flying along and you see an anvil cloud and the anvil's like this, the thunderstorm is moving that way. If the anvil cloud is like this, the thunderstorm is moving that way, okay? So that is a good indication to you as a pilot of which way that thunderstorm is moving, and it tells you which way you need to go to miss that thunderstorm. Now, it is never wise to fly under the anvil of a thunderstorm, and you'll see that in just a second. So the dissipating stage is marked by a strong downdraft embedded within the area of precipitation. Now, subsiding air replaces the updraft through the cloud, effectively cutting off the supply of moisture provided by the updraft. Precipitation tapers off and ends. Compression warms the subsiding air and the relative humidity drops. The convective cloud gradually vaporizes from the bottom up, and it just leaves the anvil cloud in its wake. Now, you may ask yourself, and you may ask me, well, Shannon, how do I know if we're in the dissipating stage of a thunderstorm? It's very simple. I want you to think back throughout your life, and it's been raining or whatever, and then all of a sudden, out of nowhere, it seems like the raindrops get twice as big, 3 times as big, and it seems like it starts raining twice as hard or 3 times as hard. That's the dissipating stage of a thunderstorm. In essence, what this thunderstorm is doing, it has built up all of this energy that it cannot contain in the cloud any longer, and it's releasing it all at one time. That's the dissipating stage of a thunderstorm, okay? So let's blow this up, and let's look at it. So here you have the towering cumulus stage to your far left. Warm, unstable air is forced upwards through that lifting mechanism. As it rises through the atmosphere, it reaches the condensation level, turns into a cloud, but that lifting mechanism keeps forcing that cloud up, and it turns into a towering cumulus. It looks like a tower of a big puffy mashed potato looking cloud, okay? That's the first stage of the thunderstorm. So we move into the mature stage of the thunderstorm, where that towering cumulus cloud has now grown and has went way up into the stratosphere and shears off into an anvil cloud, and rain starts to hit the surface. Now, as rain starts to hit the surface, that adjacent air is brought downward. That is your gust front, and usually that's well in advance of the parent thunderstorm out behind it. Then we move into the dissipating stage. That cloud and that thunderstorm has built up all the energy that it can, and it's released it all at one time. It starts raining twice, 3 times as hard. The drops are twice as 3 times as big. The air compresses, the relative humidity drops, and then the bottom of the cloud vaporizes and leaves just the anvil in its wake, okay? So there is a depiction of how the stages, the 3 stages of a thunderstorm work, all right? Now, there are different types of thunderstorms that you need to be well aware of, okay? So we have single cell thunderstorms, we have multi-cell thunderstorms. Now these are sometimes called cluster and a line of thunderstorms. And we have the worst type of thunderstorm in a supercell, okay? Now, all thunderstorms are hazardous to aircraft. You need to remember this. All thunderstorms. They do not have to reach severe limits to be hazardous to your aircraft. A single cell or a common thunderstorm is also called an ordinary cell thunderstorm. Consists of only one cell. Okay, it's just one little cell thunderstorm, okay? Now, this is usually what we see during the summertime on hot, humid days. Now, these cells can be severe and produce hail and microburst winds. And, you know, we talked about the life cycle. All the life cycles of each type of thunderstorm is the same, okay? And which we just covered. Now, just because it's a single cell thunderstorm, do not think it cannot be severe, and do not think that it cannot do damage, because it very well can. All right? So, these single cell thunderstorms like we get during the summertime, they're very easy to circumnavigate. You can go around them very well, okay? This is where you have to work with ATC and tell them, you know, I need 30 degrees left, 30 degrees right to get around the thunderstorm, and they're going to let you deviate and go around them no problem, okay? Now, these are rare. Normally we get, you know, lines of storms, or we get individual cell, which are supercell thunderstorms, but normally a single cell type of thunderstorm is rare, okay? So now let's talk about a multi-cell cluster of thunderstorms. Now this consists of a cluster of cells at various stages throughout their life cycle, okay? With an organized multi-cell cluster, as the first cell matures, it is carried downwind. That makes sense, right? Well, once it's carried downwind, a new cell forms to take its place back here. So this is the multi-cell, and we see these a lot here in Arkansas. A multi-cell cluster may have a lifetime of several hours or more. I mean, as long as the ingredients are necessary, you know, for thunderstorms to form, they're going to continue to form, all right? So what is the ingredients? You need a sufficient water vapor, you need a lifting mechanism, and you need an unstable atmosphere. As long as those three ingredients are present, new cells will continue to develop. Individual cells within the cluster may move in one direction while the whole line moves another direction. This is very common. You might have a cell here that's moving northeast and the whole line's moving east. It just depends on what is pushing that line of storms, okay? Now it could cover large areas and is persistent, makes it a bit more difficult to circumnavigate. Because if that whole line is moving east and you're flying west, well, you got one that's moving northeast, so you can't go this way, and you can't go this way because you might have one down here that's moving northeast. So it makes it a bit tougher to circumnavigate. So in a situation like this, what do you think the best answer would be? Land. Wait it out. There's nothing that says you have to do it. There's nothing that says you have to fly through those storms. All right, so use your best judgment. Land, wait the storms out, okay? So let me blow this here up, and you can kind of sort of see the progression from a different standpoint. Now, as you can see up there to the right, top right of the slide, the anvil's pointing to the right, so the thunderstorm is moving from left to right. And there you see the different stages, the towering cumulus, the mature stage, the downdraft, and the dissipating stage. Okay. So sometimes thunderstorms will form in a narrow band called a squall line. We get these very, very often in Arkansas. Okay. Now the squall lines are normally out ahead of a cold front, and I told you earlier that a cold front is arced. It's arced. Okay, it's in a bow shape. Now a lot of times these squall lines will take the shape of the front. So you will have the front back here and the squall line out here ahead of the front, and as the front moves across, the squall line will move out in front of it, okay? So like I said, it often develops ahead of a cold front in moist, unstable atmosphere, but it may develop in unstable air far removed from the front. So the front may be way, way behind it. It does not have to be close at all. So new cells continually reform at the leading edge of the system with rain and sometimes hail, following behind sometimes a storm, or following behind sometimes storms which compromise the line can be supercells, okay? So in the squall line, there could be individualistic cells that are supercells, and we're going to talk about supercells here in just a minute. excuse me, but supercells are the most dangerous type of thunderstorm because they feed on themselves, okay? And you'll see that here in just a little bit, okay? Now, this line, the squall line, can persist for many hours. As long as those three necessary ingredients are there, they're going to continue to persist. What are the three necessary ingredients again? Unstable atmosphere, lifting mechanism. What's the third? Very good. As long as those three are there, these storms are going to continue, okay? These squall lines are thunderstorm types which present the most effective barrier excuse me, to air traffic because you got a line of storms. You can't go over them. You can't go around them. You can't go under them. So what are you going to do? Excuse me. Land. Wait the thunderstorm out. There's nothing so pressing that you have to risk your life or the life of your passengers. Land and wait the storms out, okay? Now, let's talk about the most dangerous type of thunderstorm, and that is a supercell, okay? Supercell thunderstorms, I know this says they're often dangerous. These are dangerous. You do not mess around with a supercell thunderstorm, okay? They are long-lived convective storms that consist primarily of a single quasi-steady rotating updraft that persists for an extended period of time. Look at those words. Rotating updraft. You hear the words rotating associated with a thunderstorm, what are you going to have? High likelihood you're going to have tornadoes, right? Very good. Now, this thing has a very well organized internal structure that enables it to produce especially dangerous weather for pilots who encounter them. Updraft speeds may reach 9,000 feet per minute. What do you think about that? Normally in your 172, you're going to climb at 500 feet a minute. 9,000 feet per minute. That's moving. And I'm sorry, but your little 172 is not going to withstand that. Now, this allows hazards to be magnified to even greater degree. Nearly all supercells produce severe weather. I want you to think about what that just said, and I want you to change it. All supercells produce severe weather. You look at it that way, you'll be safe. All supercells produce severe weather. Do not mess around with a supercell thunderstorm because you're going to have damaging winds, large hail, and this says about 25% of them produce a tornado, but I would be willing to change that. I would say 50 to 60% of all supercell thunderstorms produce a tornado. It might be short-lived, but supercell thunderstorms are the ones that normally produce violent, large, high ranked on the enhanced Fujita scale, long-lived, long-track tornadoes. I'm from Wynne, Arkansas, and earlier this year, on March 31st, we had a supercell thunderstorm that produced an EF3 tornado that wiped my town pretty much off the map. Right through the middle of town, all the places that I remember growing up as a child are gone. It's destroyed. And it was a long-lived, long-track supercell thunderstorm producing this tornado that went through my town. Do not mess around with these, okay? Now, a supercell will persist for many hours, all right? Here's a little research that you can do. You don't have to do it, but if you're interested in it, here's a little research you can do. I want you to research what was the longest lived tornado in history. And then I want you to research what's the most powerful tornado ever recorded in history. Both of those come from supercell tornadoes, from supercell thunderstorms that produced that tornado. Okay? These things feed on themselves. They draw the air and stuff in around its perimeter there, and it just continuously keeps going until it just absolutely does not have the energy and cannot tap into the energy needed for it to survive any longer. Okay? So if you're interested in that, do that research. Okay? So new cells will continue to form as long as those three main ingredients to produce thunderstorms are needed. Okay? A supercell's size and persistence make it a bit, well, it makes it tough to circumnavigate, okay? Because these things are usually 40, 50, 60,000 feet tall. I don't care if you're in a commercial airliner, you're not going to get over it, okay? And you're going to have to go a long ways to go around it. Now, here's what you need to consider. In most general aviation aircrafts, even if you're trying to go around it, you're not going to be able to go around it fast enough, okay? So the best thing you can do is, if there's a chance for supercell thunderstorms anywhere along your route of flight, change your route or don't go, one of the two, okay? So multi-cell clusters and lines may have supercells incorporated as a part of that system as well, so you really, really have to watch your weather and know what you're looking at on your charts, because if these things are popping up and they're a part of a line or a system, do not go. There's nothing worth, there's no trip or no job that you have to do that is worth your life or someone else's life trying to fly through one of these, okay? So let me blow this up. This is a picture of a supercell thunderstorm. Now, it's, you see the overshooting top there, okay? You see the anvil that's in the stratosphere. So if the anvil's in the stratosphere, the overshooting top is in the stratosphere as well. And then you have the parent cumulonimbus cloud. Now you got to think about this. This whole thing is turning. This whole thing is rotating, okay? Then you got the flanking line out behind it. That is where you're going to pick up a lot of strong winds. They're called RFD, rear flanking downdraft. And that's where the tornado there at the bottom under the wall cloud, that is that RFD that is feeding that tornado, okay? Now, you see how little that wall cloud is and that tornado is compared to the whole supercell structure. But here's what you have to understand. That whole supercell structure is feeding that tornado. That allows the tornado to become larger. Some tornadoes get up to a mile, mile and a half wide. And it also feeds the intensity of how strong the winds within that tornado are. So just because the tornado comprises just a small little area of this whole supercell complex, you have to understand that this whole supercell complex is feeding that one little small area and making it very, very, very destructive. And anywhere in the supercell complex, you're in trouble, okay? So stay away from it. There's nothing worth you flying into this, okay? So now let's talk about some factors that influence thunderstorm motion, okay? So we know that thunderstorms, they're a process, and it's not like a solid object like a block of wood or anything, okay? Storm motion equals the combined effects of advection, you need to know these terms, advection and propagation, okay? Now, advection is the component of the storm motion due to individual cells moving with the average wind throughout the vertical depth of the cumulus cloud. Now, here's how you here's some things that you can kind of put together to know what we're talking about, okay? Anytime you see the word advection, it's got to have wind associated with it. Okay, now this is going to come into play even later on when we start talking about fog. There is a type of fog called advection fog that happens along the coastlines mainly, but without wind, you do not have advection fog. Without wind, you do not have advection formation, okay, of a thunderstorm. Can't. Advection has to have wind, okay? Now, you can look at flight level 180 on the winds aloft chart. That's the 500 millibar or hectopascal range. And that'll give you a pretty good estimation of how storms are going to move, okay? Now, so that's advection. Let's talk about propagation just for a second, okay? So propagation is the component of the storm motion due to old cell dissipation and new cell development. So when you got one that dissipates and one that forms, propagation, okay? Storm motion may deviate substantially from the motion of the individual cells which compromise the storm. That's what we were talking about earlier. You might have individual cells moving kind of sort of in a northeasterly direction where the whole complex is moving west to east, okay? So let me blow this up so you can see it, and let's talk about it just for a second. So if you look at this diagram here, so you see that at time 0, we're going to call that 0 minutes, you got storm cell A with storm cell B behind it. Well, if you fast forward in time, due to advection, storm cell B now is where storm cell A was, and now storm cell A is on up the line a little bit and starting to go into the dissipation stage, okay? Now, if we look at time 20, through advection and storm motion, storm A has completely dissipated and went away. Storm B is now starting to dissipate, and storm C, who was behind storm B at time 10, is now the main storm, and storm D is starting to form behind it. Now I want you to notice, the storm motion is taking this from left to right. Now that could be, let's just say that is west to east. But the individual storms within this are moving northeast. And you will see this quite often, especially here in Arkansas, okay? So let's talk about hazards of a thunderstorm, all right? As I said, every type of thunderstorm that you're going to encounter are hazardous to aircraft. While not every thunderstorm contains all of these hazards, it is not possible, to visually determine what hazard a thunderstorm will have. You're not going to know until it's there, okay? Now, some of these hazards include low ceilings and visibility, lightning, adverse wind, downburst, turbulence, icing, hail, rapid altimeter changes, static electricity, tornadoes, and it can rain so hard, especially in a turbofan engine or a turboprop, where you can actually suck rain into the engine. So you have to really be conscious and understand what the hazards are and know that every type of thunderstorm has hazards associated with it, okay? But you're not going to know what hazards are present until you're there. So what's the best choice? Don't go into it. Stay on the ground, wait it out, okay? So let's talk about low ceilings and visibility just for a minute. So generally, visibility is near zero within a thunderstorm cloud, okay? You're not going to be able to see out the windows. And you will learn this very well when you go into next semester and start doing your instrument rating, okay? Ceiling and visibility may also be restricted by precipitation and dust between the cloud and the ground. You can fly into a rain shaft that's raining so hard, you might as well be in a cloud because you can't see. You could be in a gust front and it blowing dust around so bad that you can't see. You might as well be in a cloud. The restrictions create the same problem as a ceiling and visibility restrictions from fog, mist, things like that. But the hazards are increased when associated with other thunderstorm hazards like turbulence, hail, lightning, and it can make precision instrument flying impossible. So why chance it? Why put your life and the life of your passengers on the line when you don't have to? There's no sense in doing that. Don't ever do that. Always err on the side of caution, okay? Land, wait the storm out. So as we talked about earlier, you can't have a thunderstorm without lightning, okay? Now, lightning is a visible electrical discharge. We all know what lightning is. Now, the discharge may occur within the cloud. That's just self-contained within the cloud. It can be cloud to cloud, so lightning discharge can go from this cloud to this cloud, or it can be cloud to ground lightning, okay? So 3 types of lightning that can happen within the thunderstorm. You got within the thunderstorm cloud itself, cloud to cloud, and cloud to ground. Now, lightning can disable your aircraft. I mean, it's hot, okay? It can puncture the skins on your airplane, okay? It can damage communication equipment, electronic navigation databases and equipment. It's a bad thing. Lightning has been suspected of igniting fuel vapors, causing an explosion. However, serious accidents due to lightning are extremely rare, but just because they're extremely rare does not mean that they cannot happen, okay? So take lightning very seriously. Now, nearby lightning can blind the pilot. It can blind you. I mean, you're flying through there and all of a sudden it gets dark from a thunderstorm cloud and you get a real bright flash of lightning, you're going to have what I call electrical blindness. And that's just, we all know that lightning is an electrical discharge. Well, it's so bright that it will blind you just for a minute, okay? It can also induce permanent errors in your magnetic compass. It can screw that thing totally up, all right? Lightning discharges, even distant ones, okay, can disrupt your radio communications on low and medium frequencies, which is what your 172 runs on. So if there's thunderstorms in the area, what's the best thing to do? Land the airplane, wait for the storms to pass, okay? Though lightning intensity and frequency have no simple relationship to other storm parameters, severe thunderstorm, they're going to have it. As a rule, they have a high tendency of lightning, okay? So just think in your past severe thunderstorms that you have lived through, think about the lightning associated with them. There was quite a bit, right? So just remember that. So here are a couple of things that are very dangerous to aircraft when dealing with thunderstorms. Downburst and microburst. Now, the downward movement or downward column of moving air in a thunderstorm, they're usually large, okay? Convective clouds, shower cells, and thunderstorm cells sometimes produce intense downdrafts called downbursts that create strong, often damaging winds and wind shear. There have been major airline crashes due to this very thing right here. And I would encourage you to just Google airline crashes due to downburst or microburst. There was one that happened in Dallas where an airline tried to fly through a microburst and they slammed the ground and slid into the fuel tanks and it killed several people, okay? Now, these are generally smaller and short-lived, and these downbursts are called microbursts, all right? You will be able to tell, now we have sensors and stuff that tells you of low-level wind shear or downbursts and stuff like that at your major airports. We don't have anything like that here at Melbourne. We're just too small. But pay attention and just know that if you have thunderstorms in the area, microburst is a very high possibility, all right? So again, What's the best thing to do? Land, stay on the ground, wait for the storms to pass. There's nothing, you're going to hear me say this quite often, there is nothing worth your life, the life of your passengers, nothing. Don't go. Stay on the ground. A microburst is a small-scale, intense downdraft that when reaching the surface spreads out symmetrically or asymmetrically, it don't have to be symmetrically, in all directions from the downdraft center. It is the most severe type of wind shear. Microburst activity may be encountered as an intense rain shaft at the surface or virga. Now, virga, I'm going to give you a little quick definition and explanation of virga. You will see this quite often, but if you look up in the sky, or if you're flying and you see a cloud and it looks like it's just got fingers or little octopus tentacles hanging off the bottom of the cloud, that is virga, okay? At the cloud base and or ring of blowing dust sometimes is the only visible cue. So what that's saying is, if you see that virga, that could be a downdraft or microburst, okay? Now sometimes looking at the bottom, you might not see a rain shaft. All you'll see is it'll look like a storm cloud up there, nothing, and then you'll just see dust blowing up from the bottom of it. It's a microburst. Don't go near it. A typical microburst has a horizontal diameter of less than 2.5 miles and it has a normal depth of 1,000 feet. So that means that the microburst is from 1,000 feet in altitude down to the surface only. Typically, let me say that. The lifespan of a microburst is about 5 to 15 minutes, during which time it can produce downdrafts in excess of 6,000 feet per minute. Again, can your 172 withstand 6,000 feet a minute? No, it cannot. Now, if you try to fly through a microburst, you're going to have an increasing headwind, and then that headwind's going to shear off as you go through it to a tailwind, and a loss of 30 to 90 knots can be expected. Now let's think about this just for a second. If you're coming in on final, what speeds are you flying? 75, 70. Cross the fence at 65. What's going to happen if you lose 30 knots? You just stalled less than 500 feet from the ground. Are you going to have time to recover? Don't do it. You're not going to recover, okay? So, more than one microburst can occur in the same weather system. It's not a one and done deal, okay? So you're cautioned to be alert for additional microburst if one has already been encountered or observed. Just because one happens does not mean that you're out of the woods, okay? It could happen again. If several microbursts are present, a series of horizontal vortices can form near the ground due to severe microbursts being embedded in one another. Now, well, Shannon, what does that mean? Well, that means we all know that this is vertical, this is horizontal. So if you have more than one in a given area, it can look like a sideways tornado coming off of it. So if you see that, you know what's happening, all right? Conditions associated with these vortices may produce very powerful updrafts and roll forces in addition to the downdraft. So basically what you're going into a sideways tornado. You're going to have vertical, horizontal, and rolling motions, all right? Your little 172 is not going to withstand that. Do not fly anywhere near it, okay? A downburst or a microburst is dangerous to aircraft when climbing from takeoff or approaching the land. That's what we were just been talking about. During these phases, the aircraft is operating at slow speeds, and a major change of wind velocity can lead to a loss of lift and a crash. That's what we were just talking about. During landing, if the pilot reduced power and lowered the nose in response to a headwind shearing off, that leaves the aircraft in a nose low, power low configuration when the tailwind shear occurs, which makes recovery more difficult. I would bet to say nearly impossible. It's not worth your life or the life of someone else for you to try to be, a hero and fly through this, okay? It's going to cause the airplane to stall low to the ground, and you're either going to crash or land short of the runway. Do not do it. So you should be alert for indication of microburst early in the approach phase, okay? And ready to initiate an missed approach at the first indication. At the first indication of a microburst, you pour the power to it and you try to get above it, okay? Now, it may be impossible to recover from a microburst encounter at low altitude. We had just talked about that. You're probably not going to recover from it, so what sense does it make to try to fly through one? There's nothing that important, okay? Now, you should be aware of asymmetrical microbursts, since significant airspeed increase may not occur upon entering the outflow, or it may be much less than subsequent airspeed loss experienced when flying or when exiting the microburst, okay? It is vital that you recognize that some microbursts cannot be successfully escaped, no matter what you do. There's some that you just can't get through or get around, so why chance it? Don't do that. Do not ever fly through one. Some wind shears that are within the performance capability of the aircraft have caused accidents. So what that is saying is that just because you encountered a wind shear that your aircraft theoretically should be able to handle, it has caused accidents in the past. Why chance it? Do not do that, okay? Do not fly through a microburst if you don't do it, okay? So let's talk about some thunderstorm avoidance. All right, so the FAA gives us some very specific things that we need to think about in thunderstorm avoidance. So let's look at these, okay? Never regard any thunderstorm lightly. Even when radar observers report the echoes are light in intensity, that does not matter. All thunderstorms are hazardous to aircraft. Avoiding the thunderstorm is the best policy. The following is guidance from the FAA for avoiding thunderstorms. Do not land or take off in the face of an approaching thunderstorm. A sudden gust front of low-level turbulence cloud could cause loss of control. You are going to know well in advance through your pre-flight planning through ATC that you've got storms ahead of you. If you have storms ahead of you, land the airplane at a spot where thunderstorms are not present yet and wait on them to pass, okay? Do not ever attempt to fly under a thunderstorm, even if you can see through to the other side. Do not do it. Turbulence and wind shear under the storm could be hazardous. Do not attempt to fly under the anvil of a thunderstorm. There's a potential for extreme, that CAT stands for clear air turbulence. Now, I'm going to pop myself back on the board just for a second because there's something I want to add to this, okay? So we know that in a thunderstorm we have updrafts and we have downdrafts. We have updrafts, we have downdrafts. Where do you think hail comes from? I want you to think about that just for a second. So all hail is a frozen water droplet that gets banged around in that thunderstorm, updraft and downdraft. The more cycles it goes through on the updraft and downdraft, the larger the hail, okay? Now, that anvil can discharge hail from the core of that thunderstorm, up to 30 nautical miles from the anvil. Now, you're going to see here in just a second that the FAA recommends that we avoid thunderstorms by 20 nautical miles. But I want you to think about what I just said. The anvil can discharge hail up to 30 nautical miles from the thunderstorm. But if you only have to circumnavigate by 20 nautical miles, can you still be hit by hail? Yes, you can. So I would say miss that thunderstorm by at least 35 to 40 nautical miles. That's what I would say. But I'm not the FAA, so let's continue. Do not fly without airborne radar into a cloud mass containing scattered embedded thunderstorms. Scattered thunderstorms, not embedded, usually can be visually circumnavigated. So if they're just scattered thunderstorms, don't fly into them, you can get around them, okay? Do not trust the visual appearance to be a reliable indicator of turbulence inside a thunderstorm. You can't see turbulence. Do not assume that ATC will offer radar navigation guidance or deviation around thunderstorms. Okay? You as VFR pilots, you should be requesting flight following. ATC does not have to give you flight following. And if thunderstorms are present, they're probably going to be busy with IFR traffic. 9 times out of 10, you're probably not going to get guidance from ATC unless they are just absolutely not busy, and then they can deal with you, okay? So don't rely on that. Use a data-linked weather radar, NEXRAD radar, mosaic imagery as the sole means for negotiating a path through a thunderstorm area, also called tactical maneuvering. Now, let's think about this. And I know you don't know anything about NEXRAD radar, but you're fixing to learn the most important thing that I can teach you about NEXRAD radar. Do not trust it. Don't trust it. Well, Shannon, why? It's radar. Why shouldn't I trust it? For the very simple fact, that image that you're getting inside your airplane on your GPS, it's anywhere from 7 to 15 minutes old. It's not current. Do not trust NEXRAD radar. You can use it in pre-flight planning, but when it comes to getting around thunderstorms, don't trust it. Do not trust it. Remember that the data-linked NEXRAD mosaic imagery shows you where the weather was, not where it's currently at. Okay? Now this says it could be 15 to 20 minutes old. That sounds even better to me. Normally they're 7 to 15 minutes old. Don't trust it. Okay? Listen to the chatter on the radio. Listen for PIREPs and other aircraft requesting to deviate or divert to get out of it. Use common sense, folks. If you've got a 737 that's requesting to deviate around storms, you might want to take your little 172 and put it on the ground. Because that 737 can withstand a lot more than that little 172. And if he's wanting to get out of it, you better be getting out of it. Okay? Ask ATC for radar navigation guidance or to approve deviations around a thunderstorm if needed. Now again, you cannot rely on this because if they are too busy, guess what? They're not going to help you. Okay? They're not required to. Like I said earlier, just use that NEXRAD for route selection. Okay? That's fine to use it for. That's in your pre-flight planning, but don't use it to strategically maneuver around thunderstorms. Advise ATC when switching to another controller that you are deviating for thunderstorms before accepting to rejoin the other route. Now, what that is talking about, and I know you guys probably, well, this is your 3rd week of class now. I know you don't know about this yet. So as you're flying along, if you are on flight following and there are thunderstorms in the area, you can ask ATC for a diversion, because when you get flight following, they're going to take you from where you're at to where you're going in a straight line. Okay? And that's what they expect you to fly. So if you need to divert around a thunderstorm, you're going to ask them for permission. Well, they give it to you. Now, let me put this back up. So they give it to you. Now, they know that there's a thunderstorm here and you're flying over here to go around that thunderstorm. Well, right in here, you have to switch controllers. That new controller is, all he knows is that you were here and you're going over here and there's a thunderstorm here. So when you switch over to that new controller, you got to let the new controller know, hey, I'm up here, I'm going around this thunderstorm that's right here, and as soon as I can, I will go direct back to where I was supposed to be going, okay? You have to keep them up to date on what you're doing, all right? So ensure that after an authorized weather deviation by ATC, and before accepting to join the original route, that the route of the flight can be clear of thunderstorms. So when you get around that thunderstorm, before you tell ATC, okay, I'm going direct back to my destination, make sure that you can do that without flying into a thunderstorm. Now, here's the big one, okay? This FAA says avoid thunderstorms by at least 20 nautical miles. Now, it says when they're identified as severe or giving an intense, heavy, or extreme radar echo. I don't agree with that. I do not agree with that. I want you to avoid A, by 35 to 40 miles, and B, every thunderstorm. I don't care if it's light or not, you avoid it, all right? They say that this is especially true under the anvil of a large cumulonimbus cloud. Such echoes should be separated by at least 40 miles before trying to fly between echoes. Now, what does that mean? All right, so let's say that we have a thunderstorm here. We got a thunderstorm here. Between here and here, this gap, there should be at least 40 miles between the two before you try to split that gap, okay? All right, circumnavigate the entire area if more than half of the area is covered by thunderstorms. Go completely around it. Vivid and frequent lightning indicates the probability of a severe thunderstorm. Regard as extremely hazardous any thunderstorm with tops of 35,000 feet or higher, whether the top is visually sighted or determined by radar. If you see an echo, and you will see this on weather maps and stuff like that, and it says 350 in the middle of a storm, that's telling you that that thunderstorm top is at 35,000 feet. You stay away from it. Give a flight PIREP for your flight conditions. Divert and wait out the thunderstorms on the ground if unable to navigate around an area of thunderstorms. It's what I was telling you earlier. It's better to land and get on the ground than it is to try to do something stupid and get yourself hurt, okay? Now, this week's quiz, the password is thunder. All capital letters, thunder. You will need to, just like last week, you will need to put this password in before you can take the quiz. It will be a 20-question quiz, okay? So, going on with thunderstorm avoidance, all right? If you are unable to penetrate a thunderstorm, or avoid penetrating a thunderstorm, this is the following guidance from the FAA that they say you should do, okay? Tighten your seatbelt. Well, that's a gimme. Put on the shoulder harness if installed. Well, it should be on anyway. And secure all loose objects. Why do we want to secure loose objects? Well, in a thunderstorm, those loose objects just become projectiles. And if you got a thermos that's made out of metal, you got a missile in there with you. I don't want to get banged in the head with that. Do you? Well, if you do, maybe you're tougher than I am, but I don't want to get banged in the head with it. Okay? Plan and hold the course to take the aircraft through the storm in the least amount of time. To avoid the most critical icing, establish a penetration altitude below the freezing level or above the level of 15 degrees Celsius. Okay? Verify that your pitot heat is on and turn on your carb heat, or if you're in a jet engine, turn on your anti-ice. Icing can be rapid at any altitude and cause almost instantaneous power failure and or loss of airspeed indication. Establish a power setting for turbulence penetration airspeed recommended in the aircraft manual. Now, in your 172, that recommended airspeed is your maneuvering speed, VA, okay? Now, if it's just you and the aircraft full of fuel, it's probably going to be around 88 knots. If it's you and an instructor full of fuel, it's probably going to be around 92 knots, okay? But what's going to happen is you're going to trim the airspeed and trim the airplane and get it set at or below your maneuvering speed, okay? I would prefer at your maneuvering speed, all right? Now, as you fly into a thunderstorm, you have to remember there's updrafts, there's downdrafts. You're going to have all kinds of motion going on within that thunderstorm. So hold your wings level. Keep your wings level. That's called flying a constant attitude. Hold your wings level at maneuvering speed or thunderstorm penetration speed, whichever is recommended by the manufacturer, and you accept altitude changes. Okay? You're going to go up, you're going to go down. That's fine. You accept all of that. Wings level, constant attitude, maneuvering speed, or thunderstorm penetration speed, whichever is the right thing for your airplane. Okay? Turn up the cockpit lights to the highest intensity. During the lightning flashes, it lessens the temporary blindness from lightning. Okay? If you're using the autopilot, turn it off. Turn it off and hand fly the airplane. Okay? If you don't, it increases the chances of structural stress on the aircraft. If using airborne radar, tilt the antenna up and down occasionally. This will permit the detection of other thunderstorm activity at altitudes other than the one being flown. Keep your eyes on the flight instruments. Looking outside the cockpit can increase danger of temporary blindness for lightning. Focus on your instruments, okay? Do not change the power setting. Maintain the settings for turbulence penetration airspeed. Maintain that constant attitude that I was just talking about and allow for altitude and airspeed fluctuations. You're going to go up, you're going to go down, your airspeed's going to go up, your airspeed's going to go down. Accept all of that. There's nothing you can do to stop it. You keep that constant attitude, wings level, okay? Now, don't turn back. Once you get in it, get through it as quick as you can. Do not turn back. A straight course through the storm most likely will get the aircraft out of the hazardous situation quickly. In addition, turning while you're flying through a thunderstorm increases the stress on the aircraft. Wings level, constant attitude, fly through and get out of it, okay? But don't ever let yourself get into it. Don't ever let yourself get into it. But if you do for some reason, get through it as quickly as possible, okay? Now, this concludes our lecture on thunderstorms. Guys, these things are dangerous, all right? I want you to remember that all thunderstorms are hazardous to aircraft, okay? Now, as in every week, you have a quiz that you have to take. I gave you the password for that, okay? So go and take your quiz. Now, I need to stress everything that's covered in these lectures are subject to be questions on your quiz. So know the material, okay? Other than that, guys, make sure you do your quiz and your discussion posts. And remember, everything is due by 11:59 this Saturday night, okay? And I really hope you have a great week. And we'll see you next time. Bye-bye.